This video is for Module 2, Part 9, and includes a discussion of using the normal distribution to construct a confidence interval for a proportion. Okay, let's go ahead and get started. So as we talked previously, there are some limitations to using a simulation model to obtain a reference distribution. For example, different people will get slightly different reference distributions, which will produce slightly different confidence intervals. The most common approach to computing a 95% confidence interval for a single proportion is to use the normal approximation to this reference distribution. The approximation using the normal distribution works well in most situations. In cases where the reference distribution is pushed too low or too high, then the normal approximation should not be used. In such cases, the confidence interval should be obtained directly using the binomial probability distribution. Okay, so let's talk about the normal approximation. Consider again the outcomes from the Star and Tribune poll regarding the support and opposition of gun control laws in the United States. We looked at this example in the previous part. There were a total of 625 people in this poll, and 350 supported such laws. So if we take 350 and divide by 625, we end up with that 56%. We can use the reference distribution app to obtain that reference distribution. We simply input the probability of success to be the 56%, the sample size to be the 625, and here I've obtained number of repeated outcomes of 10,000. You can see from the reference distribution that it does tend to follow a bell curve, or what we call a normal distribution, and that's what we're going to discuss further here. The center of that bell curve is right at that 56%, the proportion from the sample. The bell curve and also the binomial probability distribution is actually based on the number of samples being infinite. So what that means is if two different statisticians construct confidence intervals with this method, they will get exactly the same result. So how do we go about getting the margin of error in a confidence interval when using the normal distribution? Here's a table that constructs the various values and formulas that will be used. So again, we're going to use our statistic, which is just the proportion from the study. That's denoted by a pi hat value. The upper margin of error here is just simply 1.96 times the square root of pi hat times 1 minus pi hat, all divided by n. The lower margin of error is just that same quantity, except I'm going to use minus 1.96 instead of the positive 1.96. The upper end of the confidence interval is simply computed by taking the statistic, which is the pi hat value, and then adding on that positive margin of error. So that 1.96 times the square root of pi hat, 1 minus pi hat, all divided by n. The lower end point is similar in that I'm going to start with the statistic, and I just go down that same distance, that margin of error distance of 1.96 times the square root of pi hat times 1 minus pi hat, all divided by n. I'm going to show you how to let a spreadsheet do all of these calculations. You can certainly do these on your calculator, but a spreadsheet will be a little easier and will allow us to compute these quantities. So let's look at just a schematic with the reference distribution that I obtained up above. So the middle of that reference distribution here sits at that pi hat equal 56%. And then from that middle, I have my positive margin of error, and then I also have my negative margin of error going this direction. And again, there's that quantity for the margin of error. And when I take the middle of the distribution, so pi hat plus the positive part of the margin of error, I end up with the upper end point of my interval. Here it looks like it's going to be pretty close to 60%. Likewise, for the lower end point, I simply take my proportion that I started with, which is that 56%, and I use the negative margin of error to obtain the lower end point. Okay, just some quick comments here. This pi hat times 1 minus pi hat all divided by n, the square root of that quantity, that is commonly referred to as the standard error. And as soon as I multiply that by this quantity, which we call the 1.96 quantity here, the interval multiplier, as soon as I multiply that standard error by the interval multiplier, we call that quantity the margin of error. This here includes some discussion of the interval multiplier. As I've stated here, we are going to use 1.96. 1.96 ensures that we end up with the middle 95% of the normal distribution. If I have the middle 95%, that means I'm going to be truncating 2.5% on the lower end and 2.5% on the upper end. I have provided a link here about additional information regarding the use of 1.96 as the interval multiplier. Most standard statistics textbooks will talk about other percentages that you can use. So suppose I wanted a 90% confidence interval instead, my interval multiplier would be 1.645. If I construct a 90% confidence interval, that means I'm going to be truncating the lower 5% and the upper 5% so that I'm left with 90% in the middle. We could also construct 99% confidence intervals. But far and away the most popular is the construction of 95% confidence intervals, and that is because it coincides with the commonly used 5% outlier rule. So here in this class we will simply be using 1.96 as the interval multiplier. Here's a little bit of a discussion about what can happen if that binomial probability distribution gets jammed down too low. We can see that if I were to put a bell curve or a normal distribution over the top of that, kind of the left chunk of that normal curve will get truncated off here. The binomial probability distribution cannot go down below 0, but if I were to put a bell curve over the top of that, some of that bell curve would want to drift down here below 0. Here on the screen is a commonly referred to guideline on whether or not the normal approximation is a good idea. Okay, some questions then. So let's consider the formula for the margin of error again. I've written this as plus n minus 1.96 times the square root of pi hat times 1 minus pi hat all divided by n. So question number 1. What happens to the margin of error when the sample size increases? So what happens to the margin of error as the value of n increases here? If n gets very, very large, then that means that this fraction here is going to get very, very small. And when I take the square root of that small value, it's still going to stay small. And I multiply that one by 1.96. I'm still going to end up with a fairly small value. So if you want to make your margin of error smaller, what you can do is increase your sample size here. Question number 2. What happens to the margin of error when I increase the interval multiplier? So if I used, say, 2.575, and this value would be coming from a 99% confidence interval instead of a 95% confidence interval. This value is provided in that table up above for a 99% confidence interval. If I were to use that in this formula, what that's going to do is increase the margin of error. It's going to make the margin of error slightly larger. How about the formulas for a 95% confidence interval? We have the upper end point again being pi hat plus the margin of error, and the lower end point being pi hat minus the margin of error. Again, pi hat is just the outcome from the study. So question number 3 just asks again about what would happen if I change this from a 95% confidence interval. So 95% confidence interval, I'm going to be using plus or minus 1.96 there. What would happen if I changed that to a 99% confidence interval? Well, for a 99% confidence interval, I'm going to be using plus or minus 2.575, I believe it was. So when I go from a 99% confidence interval from a 95% confidence interval, what's going to happen to these endpoints? What's going to happen is that they're going to get further apart because I'm using a larger value here. And this question asks, why does that intuitively make sense? So I'll let you try to answer that. After you provide your answers again, my solutions will be provided so you can check how you did there. Here's a common incorrect interpretation of a somewhat common incorrect interpretation of a 95% confidence interval. It goes something along the lines of, we are 95% certain that the outcome from the study will stay between the lower endpoint and the upper endpoint, whatever that might be. And that's not true. That's not correct. We are 100% certain that the outcome from the study is going to stay between the lower and upper endpoints of my confidence interval. And again, I'll let you try to answer that and figure that out. A solution will be provided. Okay, so let's go ahead and use the formulas to show you how to get a margin of error for the Star and Tribune poll. So again, the number of people were 625. The proportion or observed proportion from our study was the 56%. So here's just plugging, showing on the screen here, just plugging those values into the margin of error formula. So using 1.96, the pi hat is 0.56 here. I take 1 minus the 0.56. My sample size was 625. Going through those calculations, I get a margin of error of about plus or minus 3.9%. So how do I use that margin of error to obtain a 95% confidence interval? I simply need to take pi hat plus that margin of error. So my pi hat was 56% plus that 3.9%, and I end up with 59.9%. The lower endpoint is just going to be that 56% minus the 3.9%, and I get a value of 52.1%. Oftentimes these confidence intervals are written as I have highlighted here. So that parameter value again is just going to be the proportion of all Minnesota voters who would support stricter gun laws. That's what that pi is representing. Now, I don't know what that proportion is for all Minnesota registered voters, but I know that that value should be, or at least I'm 95% certain, that that value will be between 52.1% and 59.9%. Okay, so here's just showing you how to get those values in a spreadsheet. So I have both these support 56%, oppose the 31%. And all you need to do in a spreadsheet is just type equal 1.96 times SQRT. Okay, so I need the square root of 0.56 times 1 minus 0.56, all divided by 625. You got to make sure you got all the parentheses in there that you need. Otherwise, it won't calculate it correctly. And when you do that, we get 0.039. We can use that then in these formulas here to obtain the lower and upper confidence intervals. So there's that 52.1% and the 59.9%. You can quite easily add that margin of error to this bar. So this is the bar for support here. Again, it's at that 56%. So I show you here, I just give you a little screenshot of how you can add that margin of error bar to your bar graph if you'd like. I'm not going to show you that here. I'm not going to ask you to do that on a homework. So I'll just skip over that. But it's pretty easy to add that margin of error bar to the top of those bars. Okay. How about example 2.9.2? So what we've done here is we've taken the information that we had on the poll previously. The Star Tribune actually gave us a breakdown of how people responded in two different age groups. They also did this by gender and by race as well, but I've decided to look at the two age groups here. So one of the age groups is the 18 to 49-year-olds, so kind of younger people. And here's the breakdown of their numbers here. 176 support, 75 oppose, and 48 were undecided. If we look at the 50 and older age group, the breakdown is 172, 120, and 32. There are slightly different number of people in those two age groups, and that's fine. What I've done here is just computed the proportion in each age group that support, oppose, or are undecided. So 59% here in that 18 to 49 age group would support stricter gun laws, whereas that proportion drops slightly, just a little bit, to 53% for people that are 50 and older. So here's the bar graph for the two different age groups here, also across the different possible outcomes: support, oppose, or undecided. So the blue bar here is the 18 to 49-year-olds, and then the red is the 50 and older group. Now for the people that we have surveyed, we can see that more of the 18 to 49-year-olds, or a larger proportion of the 18 to 49-year-olds, would support stricter gun laws than the 50 and older age group. I can see that here at the top because the blue bar here for support for the 18 to 49 is slightly bigger than the red bar for support. But this is just communicating what happens for the people, or what happened for the people that we've surveyed. One thing that we might be interested in is whether or not I can say that the 18 to 49-year-olds support stricter gun laws more than the 50 and older age group. Not just for the people that I've surveyed, but is that true in general? Or can I say that the 18 to 40, can I say that a majority of the 18 to 49-year-olds support stricter gun laws? Again, not just for the people that I've surveyed, but in general. For the people that I've surveyed, I know it's 59%. But can I say that in general? If the margin of error associated with that blue bar does not drop below 50%, then that statement would be true. If that margin of error for that blue bar drops down to, say, 48%, and then it's also going to drift upwards as well, but if it were to drop down to 48% here, then I cannot make the statement that a majority support stricter gun laws in that age group. So those margin of error bars are nice when you are necessary when you're trying to make inferences about the larger group and not just the people that you've surveyed. Okay, here shows the calculations for those two different age groups. The calculations are identical to what we did up above. I just need to be careful that I have the number of people in each age group has to be put into this formula, and then obviously the different percentages for the 59% and the 53%. So here I'm attaining, just for the support, so I'm obtaining a margin of error value for this blue bar up here and also the red bar here are the two margin of error values that I'm obtaining. The margin of error for each group is the 18 to 49-year-olds is 5.6%, and the margin of error is just a little bit below that for the 50 and older group. The 50 and older group had just a few more people in it, 324 versus the 299, and that has an effect of driving down that margin of error slightly. If we look at the confidence intervals for each group, for the 18 to 49-year-olds, it goes from 53.4% up through 64.6%. So I've sketched those here on the screen as well. This is the bottom one is for the 18 to 49-year-olds. So that goes from 53.4 up through 64.6. For the older group, it goes down to 47.6 up to 58.4. One thing we notice when we look at the margin of error here is that there's quite a bit of overlap between these two groups. So what that means up here on the original bars is that I cannot be certain that the blue bar is going to stay above this red bar. When I try to make inferences about all registered voters in Minnesota, I cannot be certain that the blue bar will stay bigger than the red bar. Some other things that I notice is that I can be certain that for the younger age group, a majority are going to support stricter gun laws. Again, kind of that lower end for what I would expect that proportion to be does not reach 50%. That lower edge of that distribution does not go below 50%. So it is fair to say that a majority of the Minnesota registered voters between the ages of 18 and 49 would support stricter gun laws. So question 5 down there is yes. Again, because that lower end point does not reach down to 50%. I'll let you answer question number 6 and number 7. Okay, some final comments regarding margin of error. This first bullet here, the margin of error formula uses n, which is the number of people surveyed in the poll. The margin of error formula does not use the size of the group associated by the scope of inference. So for example, suppose the Star and Tribune decided to take a sample of all registered voters in the entire United States. So not just registered voters in Minnesota, but the entire United States. Now certainly the number of people contained in this new scope of inference is much, much larger. However, the margin of error for that poll, again if they were to use a representative sample of 625 people, would remain at about 3.9%. Because of the size of the scope of inference isn't used in this formula. If it's again about 625, then that margin of error is going to be about plus or minus 3.9%. So the only thing that influences the margin of error is how many people you put in your poll, not the size of the scope of inference. Another common misconception is that if I want to cut my margin of error in half, I have to double my sample size. And that's not true. You actually have to quadruple your sample size. And the reason is that this margin of error formula has a square root in it. So the algebra here shows you that that's the case. That in fact, I need a sample size 4 times larger if I want to cut my margin of error in half. This last bullet here is for the calculation of sample size. This is a somewhat common thing that we do as statisticians. So what is the calculation of sample size used for? So the expression is useful when a sample size calculation is needed. That is, this formula can be used to determine how many people should be included in a study in order to achieve a certain margin of error. So let's suppose that somebody wants a poll and they want to have a margin of error of plus or minus 3%. So they're going to conduct a study and they want to be within plus or minus 3%. So margin of error is 0.03 here. They also believe that the outcome from the study is going to be approximately 28%. So sample size calculation does require an initial estimate of pi hat. So they've determined that that's going to be about 0.28 or 28%. So I use those values in this formula. I'm going to put in pi hat of 0.28. I want my margin of error to be about 0.03. And going through that formula, we can find out that I need looks like about 860 people in my study. So if I were to put 860 people in my study, I would end up with a margin of error of 0.03. or at least close to 0.03. Okay, that does it for our discussion of Module 2, Part 9, the use of the normal distribution for computing a 95% confidence interval for a proportion. Thank you.